questions, please? Okay. Any questions? All right, so let me, I wanted to, so we're talking about symmetric matrices lesson. We're going to start at the same. I want to go over that. Okay, so you need this matrix here. Yes. So notice this is symmetric matrix, right? Because of course what goes down the diagonal doesn't matter. I just said anything willy-nilly. If these two match, so it's symmetric about this main diagonal, right? All right. Well, the first thing, what I want to do is I want to diagonalize this, right? And the way we're diagonalizing it is kind of really rather naturally. I want you to just notice it makes come along. And, we kind of went over this a little bit last time, but what we get with this polynomial here, when we work it all out, is we get right. And so what we have to do is we actually have to find roots for this. And this is something a little bit of a tricky thing, but you all know I discussed the rational root test with you. It turns out the only roots of this polynomial are rational. This actually has one real root that may not be right. At least one real root may not be right. But it turns out this case like the factor of the tail about a factor of the lead. Right. So the only possible rational roots are the only factors of 2 or plus or minus 2, and the only factors of negative 1 or plus or minus 1. So you really only got 4 things to check. Otherwise, you're kind of holding. And there are 2, negative 2, 1, negative 1. And actually, if you plug in 2 here, this factor, right, or this has a root, right? That means that, so let me do it up here. I find it less confusing to do this way. Notice the root of this is the same thing as the root of this. We just change the signs. Notice that 2 is root of this. So we get that. And I get lucky again because this is now what we have here is we have eigenvalues 2 and negative 1 multiplicities. So I'll write it out that way. So let's go through and find some. Yes.
The characteristic polynomial in this board is negative lambda cubed plus 3 or plus 3 lambda plus 2. Or never mind.
Are you okay? Yeah, I just changed the sign from here to here. It makes it easier for me to find. But So let's go through and find eigenvectors for this. Let me do land equals 2, the one that's just kind of by itself first. And what we're doing is we look at null space for the matrix. What happens when lambda is 2? So this is -2, 1 minus 1. This is 1 minus 2, minus 1, minus 1, minus 1. All right, so we're looking for null space here. This is kind of a sort of theme going over again. So let me do quick. I'm going to move this up to the top, change the sign. And then I'm going to use this to take out the other one. So let's see if I just add this to this, I'm going to get 0, -3, -3. And I'm going to multiply this by -2 and add to this. 0, 3. Notice these two rows are essentially the same, but I can figure this out. So I can further simplify this. Right? Just make that a pair of ones, take that out, and I've got this. And now you get a row reduced echelon form. I just got to understand. So row reduced echelon form. Right, okay, so what do we get here? Well, so I get an eigenvector out of this. 2. And I'll kind of report what I've got going on here. So I get x3 is 3. And I get the equations x2 plus x3 0, and the top one is x1 plus x3 0. So I get an eigenvector that looks like so let's kind of keep track of what we got here. 4 lambda equals 2. I get the eigenvector. Actually, I don't know nonsense. Let's do this. I can change the sign of the eigenvector. Okay. Now that I've done that, let's investigate what happens with the eigenvector. -1. Now, one of the things that I hinted at is symmetric matrices are diagonalized. Right? And the matrix I started with was symmetric. So can anybody make a prediction what needs to happen with lambda equal -1? We should be able to find 2 linearly independent eigenvectors. So my guess is when I do this matrix reduction, I know I'm going to be on the right track if I have 2 free variables, right? So let's see what happens. When you subtract -1 from this, I get 1, 1, -1. 1, 1, -1. That's a good start. And -1, -1, 1. Notice all 3 of those rows are essentially the same. Agree? Because this was just the opposite side of this one. So this reduces rather quickly. 1, 1, -1. And how about them apples? I have 2 free variables, right? typical eigenvector here looks like x3 and x2. They're both free, there's nothing I can do about them. And then x1 should be minus x2 plus x3. So I get, let me just kind of write down my two eigenvector. And again, I'll reverse the sign of this one. By the way, does anybody know a relationship? Notice the relationship between this eigenvector and the other two. That is correct. Notice that this one is orthogonal to this, and it's also orthogonal to this. This is kind of a prediction we made last time. I mentioned that the eigenspaces actually have to be orthogonal. It's not true in general, but with symmetric matrices, it's true. Now, let me ask you this. Are those two orthogonal? No, because their dot product, their inner product, when we fancy about it, is not zero. Correct? Well, we can make them orthogonal, can't we? Right? We can use Graham-Schmidt on this. So let's turn this. So my eigenspace for lambda equals -1, it certainly has those two vectors as basis. But I don't like this basis. I'd like to do a little better. Let's make an orthogonal basis. And we can just Graham-Schmidt, or since there's only two, we can think this projection. So let's kind of refurbish this and make them orthogonal. Let's let x1 be 1 minus 1, 0. And x2 equal 1, 0, 1. Okay, so I'm just going to basically, again, sort of one step running this, if you like. And B2 is x2. So it's think of this, but I have to subtract off the projection. I'll let this like inner product here. X2 B1, B1, B1. So let's see what everything is. X2 is 101 minus. Okay, I need the inner product of x2 and b1. Well, it's just 1, isn't it? I need the inner product of b1 with itself, and that's going to be 2. And then I need b1, which is. Well, let's see what we get here. I get 1 minus a half is a half. I get 0 plus a half, I get a half. And I get 1 minus 0, 1. And 0. Oh, you know what? This is actually minus half. Everybody? Yeah, but something's missing. So the other product is 1, 2. 1 minus a half is plus 1. That's plus 1. 1. 1 minus a half. 0 plus a half. And 1. That's right. Okay. X1 is B1, X2 is this, so this is B2 is X2, 101 minus X2 B1, 1 over half. B1. Yeah. You might see mistake. Yeah. Oh, I'm sorry, Max, I can't hear you. What's that?
You wrote down the negative one.
Oh, is the negative 1 at the top?
You wrote it different.
Oh, yeah, I guess, like, my original use that. Yeah, yeah. Let's. Well, let's call that out here. So let's fix this here. Okay, so X1 is X2 is 101. So let's do this again. B1 is X1 and B2 is X2 minus inner product for X2 B1 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 X2. Okay, X2 and V1 is -1. And V1 with itself is 2 times V1. So we get here, this is going to be 1. This will be half this. Now, 0. Yeah, I was right wrong. This is, I don't know, say that later. Okay. This is 112. So notice that I can refurbish this into places right here, which is -110. And notice these two are orthogonal, which because they're not part of 0. And of course, this one's also orthogonal. That's all I need. So now that I have an orthogonal basis for R3 consisting of these eigenvectors, Notice that I can normalize this. So I'm going to change the basis to 1 over radical 2, 0 minus 1 over radical 2. I put that on. One over radical 3, 1 over radical 3, minus 1 over 3. So I'll rescale this. I'm doing the word normal here. And I'm going to normalize these two things too. I'm going to take minus 1. And I'm going to normalize this one here. Notice the length of this one's radical 6. Now notice what happens here. How do we diagonalize a matrix, right? We took the eigenvectors, so I'll just do it in this order here. 1 over radical 3, 1 over radical 3, minus 1 over radical 3, minus 1 over radical 2, 1 over radical 2, 0, and 1 over radical 6, 1 over radical 6, 2 over radical 6. And then there's the diagonal matrix. Anybody remember how we put together the diagonal matrix? Right, the eigenvalues in order of the eigenvectors put in there, right? So this one's the 2. And these other 2 are minus 1. And what goes here? The inverse of this, which is a pain in the butt. However, for this one, it's easy. Anybody tell me how to find the inverse of this? What's true about the columns of that matrix? The columns are orthonormal. So what kind of matrix is that? It's an orthogonal matrix. I know it's kind of a bad terminology. So what's the inverse of any orthogonal matrix? It's transpose. Right. So I can just write down the inverse of this. Minus 1 over radical 2, 1 over radical 2, 0, 1 over radical 6, 1 over radical 6, 2 over radical 6. And yes.
Why did you need it to be more than one instead of just one body?
What are you talking about? Are you talking about the matrix or the? So what it means for a matrix to be what it means for a matrix to be orthogonal is the columns are orthonormal, right? It's an unfortunate, they should call it an orthonormal matrix. You don't. The terminology is what it is. But when you hear orthogonal matrix, that doesn't just mean the columns are orthogonal, it's orthonormal. But you need them orthonormal because you need the product of this times this to be the identity. If they were only orthogonal, then the product of this times this would not be the identity. It would have different values along. I want ones along the diagonal. But if they were just orthogonal, the other ones, perhaps. And if you multiply this out, you will get the original symmetric. So try. I'll go through more detail in the next. Any questions? Okay, so let's do another one, and this was kind of interesting, saying factorization as well. I think this was actually from your book, and the reason I'm going through this is because your book really kind of didn't do any details. You said, oh, look, here's what the eigenvectors and the eigenvalues are. I'll kind of give a little bit more message than that. So this example, let's let A be the following matrix. 6 minus 2 minus 1. 6. Okay. This matrix right here, again, is symmetric, right? Nobody cares about the diagonal, but it's paired off. So if you believe all the stuff I gave you last time, this should have, it's a symmetric matrix, so it should have all real eigenvalues. And it should have 3 linearly independent eigenvectors, right? Because it should be diagonalized. So let's go through this mess. So actually, I'm going to leave this board up here, select the facts. Let's figure out the eigenvalue. This is the most unfortunate part of the problem. This one gets a little bloody, actually. So let me kind of go through this. 6 minus x. Okay, so you got to multiply this out. That's going to be x squared minus 11x plus 30 minus 1. 29. Nobody likes 29. So this is plus 2 times, it's going to be 2x minus 10, minus 10, minus 1. And finally, minus 1 times this determinant here, that's going to be 2, and 6 is 8. And that's going to be minus x. Yes. So when you multiply this out, this becomes minus x right there. And this is 11x squared and 6x squared equals 7e x squared. And it gets worse. So this is minus 66x minus 29x, which is going to be minus 95x. Plus 4 is minus 91. Plus 1 is minus 90x. And finally, the constant term, let's see, that's 174 minus 22 is minus 162. Now there's plus 174. Minus 22 is 152, minus 8 is 154. So what we have to do is we have to factor, and just to make it easier, I'm going to change the sign of this again, x cubed minus 17x squared plus 90x minus 4. You guys see a root of that? By the way, the only roots of this are plus or minus a factor of 144 divided by plus or minus a factor of 1. So it's just plus or minus a factor of 144. There's a lot of it. You check 1 plus or minus 144 plus or minus 272, 348. It's awful. Anybody see one that works? This was a little bit less easy. Notice x equals 3. You have 27 and 270, it's 299. And on this side, it's minus 153. Or I'm sorry, 197, and that's minus 154, so that comes to 0. This has to have a factor that's minus. So that better be an x squared there. I've got a minus 3x squared, so I need minus 14x. Take that out. And if this works, this better be plus 48. That's 3 times 48, 144. Check this is x cubed minus 14 minus 17 x squared. That's good. 48 and 42 is 90x. I see that factor was left over. Of course, you can always use quadratic equation on this part. That's great. Yeah.
X. Minus 6. Thing the next minus 6.
Good. So here, what we reported we got so far. 23 eigenvalues. By the way, somebody quickly tell me, how do I know that I get 3 linearly independent eigenvectors out of this? Okay, good. All the eigenvalues are different. So all the different eigenvalues correspond to linearly independent eigenvectors. But you know what? I'm gonna make a bold claim. I started with a symmetric matrix. I will bet you that we come up with orthogonal. I can see what happens. Okay, so let's do lambda equals 3. Find the null space of this. So that is subtract 3 up diagonal here, and I'm going to get 3 minus 2 minus 1. I'm going to get minus 2, 3 minus 1. I'm going to get minus 1 minus 1, 2. You find the null space of this. By the way, that's one thing that I saw some of you notice on an exam, and I tend to be more sympathetic with partial credit when you notice a mistake. If I do the null space of this, so I do my magic and I start doing it, and I get 3 pivot columns, right? So I work on this matrix here, got eigenvalue 3, I do this, I get 3 pivot columns. What does that tell me? It tells me I made a mistake. How come? That's right. You need to get at least 1 free variable if it's honestly an eigenvalue, right? Because that means the null space has to be non-trivial. 3 pivot columns means the null space is 0, right? And that can't happen. So I hope we get a null space here. Let's rearrange this here. Let's move this to the top of the sign thing. Let's see, multiply this by negative 2 and add. Negative 2 and add. Multiply it by 3 and add. 3 and add. 3 and add. Well, that worked out pretty well. So I do get enough of the null space out of that. So 1, 1 minus 2, 0, 1 minus 1, 0, 0, 0. So I took that bottom row out and sort of flattened out the middle. And now all I got to do is this. Step. 1. Well, I'm multiply by negative 1 and a half. And let's see, that means that x3 is free, and that means x2 and x3 are the same, and x1 and x3 are the same. And it's 1, 1. And by the way, it's easy to see that this is in fact an eigenvector because if this matrix multiplied by this, you can see that. So here's what I get. I get the eigenvector 1, 1, 1 here. And again, you can go back to the original multiple test, it's not vector as well. Next, let's look at 6. Subtract 6 off the diagonal, then I get 0, minus 2, minus 1, minus 2, 0, minus 1. And minus 1, minus 1. All right, I'm gonna put these row of ones at the top, changing the sign of course. Comes -2 and add. And okay, so I get that. And -1 here. 0, 0, 0, 0, 1, 1/2, 1, 0, 1/2. So for this one, that means x3 is free. It means that x2 is a half of this, x minus half of x3. And I'm going to redo this as -1. So the lambda equals 6, I get the vector -1, -1. Notice these two vectors are orthogonal. I can dot product to see that. Finally, with the last eigenvalue 8, I bet I get a third orthogonal. Notice how, by the way, notice how this polynomial is harder. It was harder to find the roots 3, 6, and 8. But since all 3 roots are different, all of my vectors are orthogonal. That's what's spitting out. Whereas the last example where I had a double root, I had to take the basis and create an orthogonal basis from it. So at this point here, it's kind of less hard. Let's subtract 8 from the diagonal. -2, -2, -1, and -1, -1. So let's go 1, 1, 3, take the sign. Notice these two kill each other, so I've got to roll zeros up these top two. We'll multiply that just by 2 and add, I get 0, 0. And that's going to be 5. Notice I can divide out by that 5, that's very convenient. And then I can take that 3 out. Notice this means that x3 is 0, and x1 and x2 vary in sign. And so lambda equals 8, I get the vector 1, -1, 0. Again, this is orthogonal. Yes.
Or eigenvectors most often like both of ones.
You can always scale it. I promise you, if the eigenvector is not zero, then you can scale it to where one of the entries is one for sure. Because if it was 2, 4, 6, 8, you could always divide that by 2 and go, 1, 2, 3, 4. Okay. Okay, let me do the diagonal matrix first. Got 3 eigenvalues. Okay, Brian, it's your time to shine. What order would you like me to put these in? 6, 3, 8. Okay, now that Brian has made that choice, what should the columns of my matrix be? And I want to orthogonally diagonalize this. What should my first column of the matrix be? That is, you got all the details. It should be essentially this column, right? Why did he say over radical 6? That's what you keep normalizing. So the first one should be minus 1 over radical 6, minus 1 over radical 6, 2 over radical 6. How about my next column? What should it be? One over radical 3, 1 over radical 3, 1 over radical 3. The eigenvector for the second one, and of course, left with this. So it should be 1 over radical 2 minus 1 over radical 2, 0. And actually, notice on the exam, sometimes I don't ask you to find the inverse. I just ask because it's a pain in the butt to find the inverse. However, for orthogonal matrices, the inverse is easy because it's just a transpose. Multiply this out. I'll leave that as an exercise. Multiply this out on 3 of those things, and you will get the original matrix. When you started with, you will get an 8. Okay. Any questions? Yes.
Was there a reason why we spent all that time thinking it both on matrix to find the inverse instead of just finding the inverse using like other method?
Well, because you can't always just adjust the columns to make something orthogonal. If you've got columns that are not orthogonal, and in fact, with some matrices, you can't do it, right? Like the eigenvalues. So you might have a matrix that has eigenvalues 1, 2, 1, 2, and 3, right? But if it's not symmetric, what that means is the columns will be linearly independent, so you can use that to diagonalize. But you're not going to be able, but the eigenvectors may not be orthogonal, and so you can't even do that at all. In fact, sort of in reply to your question, let me get clear together. If A is symmetric and I just think eigenvalues with eigenvectors B1 and B2. Then we already know that B1 and B2 are linearly independent. That's a much older theorem. But if the matrix is symmetric and the eigenvalues are different, then they're orthogonal. So the inner product B1 and B2 is equal. Or the dot product in this case. And so stronger than diagonalizable. Here's a strong, because if we have given n by n matrix, you have n linearly independent eigenvectors, then you can always diagonalize the matrix in this order. But here's something that's a little bit strong. A is orthogonal diagonalizable. So this is sort of like diagonalizable on steroids. It's even stronger. If there is an orthogonal matrix P such that A equals P D P inverse. Will be diagonal. So in other words, you can do this not just with diagonalizable means P is invertible. So you can do this with invertible matrix. Orthogonally diagonalizable means you can do this with an orthogonal matrix, that is one with orthogonal columns. And so when you can do this, let me point this out. If you can do this, if P is orthogonal, what is another way? What does it mean for P to be orthogonal, by the way? What's the relationship? What's another name for P inverse? It's orthogonal. That is correct. Now, watch this. A is equal to orthogonal B transpose. So A transpose is P transpose. Transpose is P transpose. Transpose. A transpose. P transpose. Oops. Bring that there. That should be. P transpose transpose is P. What happens when you transpose a diagonal matrix? It's itself. And this is P transpose again. Notice that this is the same thing as A. So whenever you can do this, A must be a symmetric matrix. And actually, the converse is true. And what I mean by that is the following. There. If you have an in matrix, then A is symmetric. If and only if A is orthogonal. Diagonal. Okay. Any questions? Okay, so I'm going to talk briefly about singular value decomposition tomorrow. That'll be it. And another thing I will do, I want you all to look over quiz 21. A lot of folks struggle with it. It was like, actually, it was the lowest average quiz. And I'll work it out for you, but I want you guys to think about it. I've got it posted on my webpage. It's actually much easier, I think, than what the outcome is. Maybe you feel more comfortable with stuff now than good. But we'll talk about that tomorrow, and I'm going to shortly tell you how to do what single value decomposition value. Any questions? All right, well, we will see you all on Wednesday.